Hi, this is Dr. A from Biomechanics of Movement, 6015, Module 7, looking at the kinematics and kinetics of jumping. So in this brief lecture, we'll do a little bit of review of Newtonian physics, looking at Newton's first, second, and third law in the context of a squat, a counter-movement jump, and we're going to compare the mechanics of a CMJ and an SJ, or squat jump, and discuss some of the ways that we measure jump performance, and wrap things up with a description of Lab 6. So who's Sir Isaac Newton? Many of you have taken physics before, or at least biomechanics, and I'm sure you've ran into Newton's laws of motions, which describe the relationship between external forces and the motion of a system into three related laws. And I usually like to start off with Newton's third law because it is the reaction force that essentially causes changes in motion of the human body. The human body that is running, that is walking. We discussed, baseball pitching and how the ground reaction forces affects rotations of the body and whatnot. Well, in this case, we're looking at jumping, and if you remember, Newton's third law says for every action there's an equal and opposite reaction, and really what it is, there's an equal and opposite effect of a force that is applied to the earth. So you have Jimmy here that's sitting on top of the world, literally, and he's placing a force of, let's say, 150 pounds, and in reaction the earth is placing a force of 150 pounds in the opposite direction. However, when he starts moving, when he does a squat, or when he's landing, you only see the acceleration of Jimmy here, or more specifically the center of mass of Jimmy, because the mass of the earth is in order of 10 to the 7th kilograms. You don't see it actually accelerate. So we can measure that ground reaction force, as many of you know, using a force platform, and the ground reaction force indicates or represents the net sum of all the forces that are acting on the body, or in this case the center of mass, and therefore the change in motion of the body's center of mass is its acceleration. So let's take a look at how this all plays out using the squat. So I like using the squat because you can literally describe all Newton's first, second, and third law using the squat. So I'm just going to pause it here. Actually, I have it on the next slide. So this is the beginning of the squat itself, right there. So, gosh, there's all these ads. So the person's standing there. As you know, if the person's at rest, the net external force is equal to 0. So according to Newton's first law, it will remain in that state unless the net force acting on the body's center of mass is no longer 0, and that's now governed by Newton's second law, which says that the acceleration is directly proportional to the net force acting on the center of mass. So here we have a person on two force platforms is doing a squat. You may not see it, but this person's ground reaction force increases as the person comes back towards comes to the bottom of the squat, which indicates acceleration in a positive direction, and then comes back up. And what I show you here on the right side is the velocity of the center of mass and the acceleration of the center of mass. So just take a look at this top part right here. This is velocity with respect to time. So between t and I, the person is going into the resting position or standing position, and it's speeding up in the negative direction towards the ground, and then slows down while still moving towards the ground. It's very important that this first, between interval t and I, the individual is speeding up. That means the person is accelerating in a negative direction. And in between I and B, the person is still moving in a negative direction, but is slowing down. And because the person is slowing down while moving in the negative direction, we see here positive acceleration. Now between the intervals of B and B, this is a time interval 1 and 2 seconds. Person's actually just holding the position in the squat position and here in the bottom, and then comes back up. So you can see as it's going from the, here I'll go ahead and replay this. The person comes back down, positive acceleration there, holds it, and there's positive acceleration as the individual is speeding up in the positive direction. And as he approaches the top of the squat there, the person is slowing down while still moving in the positive direction. Hence, you see negative acceleration. Now, what does this all mean? That means that the net force acting on the individual, and when I say net force, I'm really just referring to the person's weight, which is mass times gravity, and the ground reaction force. So really what only changes is the ground reaction force. Okay? So how does this play out in relation to a counter movement jump? Here I have a counter movement jump, and the difference obviously between a squat and a counter movement jump is a person takes off. And so the person needs to create enough force on the ground and subsequently enough ground reaction force to accelerate this person's center of gravity so that the person actually takes off. So he or she actually has to take off an acceleration that is greater than 9.81 meters per second squared. So here we have person on doing a counter movement jump on a force platform, does a squat first, takes off, creates enough ground reaction force to accelerate his center of gravity that's greater than 9.81 meters per second squared. And all of you guys will be measuring this in this week's lab, and you'll see something similar to show you here. This graph that I have here, both on the left side, which is acceleration right here, and on the right side, which is the external ground reaction force. So let's take a look at this first one. This is a counter movement jump. At this point, the person's standing. The person then moves down, so that's why you see briefly the negative acceleration, right? And as the person's still moving down towards the squat, he slows down, and that's that decrease in velocity and negative velocity that's indicated here by the positive acceleration, and then positive acceleration again, in which the person takes off. And you can see how the ground reaction force is exactly the same, and that's because acceleration is directly proportional to the net force acting on the person's center of gravity. And what are the muscles doing? We're going to take a look at a couple muscles, or a couple EMG of knee extensors and plantar flexors in this particular lab. You can see when they are actually firing and when you expect them to fire. So, even though you're not quite sure what's going on with Newtonian mechanics of jumping, you can at least understand what the muscles are doing. So these are the plantar flexors, the knee extensor. This is the vertical ground reaction force. This is when the individual is slowing down first, as he's doing a squat. And what's slowing the knee flexion, as many of you know? Knee extensors. You can see that they should be firing at this point. Same with the gastroc. Remember, the ankle is dorsiflexing, so what's slowing down dorsiflexion? The plantar flexors. Eccentrically, in order to slow down that squat. And then, real briefly, as a transition from the eccentric phase to the concentric phase, these same muscles would then concentrically contract in order to create that triple extension and acceleration in the positive direction. So let's break it down again. We've got here a person just standing there, so the net force acting on this individual should be 0. It doesn't mean there's no forces acting on her. It just simply means that the net sum of her weight and the ground reaction force equals 0. Essentially, the GRF is equal to this person's weight. Okay. Then the person does the negative acceleration here that is caused by essentially her falling briefly towards the ground. That's why you see negative acceleration. She then slows down. That's indicated by here. She is still moving in a negative direction, but is now slowing down, so hence you see you expect positive acceleration, and then a brief not plateau, but a butterfly, in which she's now transitioning over from, here I can show you right here, from the eccentric phase to the concentric phase, where she's using the same muscles in order to contract and accelerate her center of mass into takeoff. Okay, so that was acceleration. So how does this look from a external force perspective? So this is the same individual. we're just going to look at the ground reaction force. So the ground reaction force here, Fz, is equal to her weight when she's simply standing there, correct? So the vector of her weight, mass times g, should equal the ground reaction force at A. At B, the ground reaction force is actually less than her weight, so therefore she has negative acceleration. If you do the math, net force equals mass times acceleration. Acceleration, therefore, would be negative when the ground reaction force is less than her weight. Now, at this point, C, I'll show you right here, ground reaction force is greater than her weight, so therefore the net acceleration is positive. But she's still moving in a negative direction, so that means she is slowing down in a negative direction. Okay, and now it's still positive in the concentric phase, which in this case the magnitude of the positive acceleration is greater than 9.81 meters per second squared, and so therefore she takes off. That literally is rocket science. So fortunately for this particular module, you won't have to manually calculate acceleration. Like I said, the software does this for you, but just understand the differences in acceleration when the ground reaction force is greater than the person's weight. It should be positive acceleration, or equal to the person's weight when the acceleration will therefore be 0, or less than the person's weight, in which in this case the acceleration would be negative. So this is illustrated here. This is Newton's second law, net force equals mass times acceleration. If we were to solve for the vertical acceleration, you could see here the instances in which the ground reaction force, Fz, when it's greater than the person's weight, would be negative. When it's greater than the person's weight, it would be positive. When it's less than the person's weight, it would be negative. And when it's equal, obviously acceleration would be 0. So it's illustrated here again. Okay. So, real briefly, just look at an example of an individual who has a body mass of 50 kilos. The ground reaction force as measured with the force platform was 1200 newtons. So if we plug in these numbers into that equation I showed you earlier, you will find out that acceleration, 1200 newtons minus 491 newtons, which is her weight, divided by 50 kilograms, which is her mass, you should get roughly 14.1 14.1 meters per second squared. Okay, with the context of Newtonian mechanics of the jump, let's take a look at the slight differences between a counter-movement jump and a squat jump. I think most of you know the difference, at least qualitatively. Right here is a traditional counter-movement jump, and the major difference is the person starts in the standing position here, which is A, where here's B. During a squat jump, the person starts in a squat position. So what are the differences here? So I've got here the ground reaction force, the acceleration of the center of mass or center of gravity, and the vertical height. So this again, A is when the person is on the ground, when the person is standing at rest, and then initiates the squat down to B. That's why you see the negative acceleration, and it slows down. And then in between C and D, the person then takes off because the acceleration here. In fact, while the person's in the air between F and H right here, you can see that acceleration should be roughly equal to negative 10 meters per second squared, the acceleration of gravity. And this, of course, is the vertical displacement of the person's center of mass, which is going to be similar to what you're going to find. So studies have shown that one of the things that makes the counter movement jump superior, if you will, to the squat jump is the activations of the so-called stretch shortening cycle, where there is an eccentric phase in which energy is elastically stored in the muscles and the tendons and ligaments, and release during the concentric phase, thereby allowing a greater torque and subsequently greater acceleration of the body center of gravity during takeoff. You can see here there's some evidence that was published in the literature in the early 90s. And during a countermovement jump, the net power illustrated by or generated during a countermovement jump was slightly higher than it was during a squat jump. And you can see here that this is the mechanical power of the stretch shortening cycle as compared to an isometric squat, as well as the squat jump itself. And you could see here for the SSC there is a slightly more mechanical power just generated. Now the mechanisms by which the stretch shortening cycle actually occurs is somewhat of a hot topic of debate, if you will. There are some camps who believe that there is no actual elastic storage that goes on there, and part of the reason is that you can't directly measure that. You can't directly measure the amount of energy, mechanical energy that is stored and released. It's only a theory. There are others that believe that doing an SSC, that the activation pattern is slightly different from different muscles of the knee extensors as well as the plantar flexors. So there's still some areas of research that need to be performed in these jumps, the CMJ versus squat jumps. Okay, so how do we measure jump performance? Well, I mean, the direct way is to measure jump heights, and jump heights can be measured a number of different ways. I posted up a article by Lithorn which describes 3 of the methods that is used to measure jump height, and more specifically the vertical displacement of the body center of mass during a jump. One is based off the impulse-momentum relationship. This is the integral, which more specifically impulse, which is the net force multiplied by some interval of time, which is directly proportional to the momentum. That's what mass times velocity is right here. So this is impulse, this is momentum, and by using this equation, we can then solve for flight time and subsequently jump height. We can also use the work energy theorem, which is just the relationship between potential energy, which is given here by the left side of the equation, and kinetic energy, which is the energy of movement. And again, you can then solve for this equation. Actually, you can directly solve for vertical displacement, which is z right here. And the flight time method, which is based off projectile equation. So this is vertical displacement, which is equal to initial velocity times time, and 1/2 the acceleration of gravity and time squared. And so if we already know that a projectile makes a parabolic shape, and we really just want the vertical displacement from, for example, the top of that parabola to the bottom, then that's simply 1/2 flight time, and you enter that number here, 1/2 gt squared. If we take it at the top, time is equal to 0. That cancels out, and you go take 1/2 g, 9.81 meters per second squared, t divided by 2 squared, and I can't type this in, but if you're taking note, this would be 1.22625 times time squared. So that is the equation that is used to calculate vertical jump height, or jump height, when you know what the flight time is. And one of the tools that you'll be using in Lab 6 is an app called My Jump, and it essentially uses flight time method in order to figure out the person's jump height when they're being filmed. It's actually really simple to use. I'll show you a video here in a sec. But the user who's recording will take the video and then indicate the frames in which the person takes off and when the person lands, and that gives us flight time. Use this little equation, the flight time, and then you get a measurement of vertical jump height. Okay, this is how it looks in Cortex. So Cortex is a person doing a free hands counter movement jump, and this is what I was talking about to you earlier. You can see here, this is the vertical ground reaction force for both the left and right side. can see as the person comes down, you get negative acceleration here, and then positive acceleration when the net force goes above the person's weight, and the person is in the air here, and then lands. And this landing part here, you can see how much transient forces occurs during impact. It's that landing force in which we try to modulate or mitigate by teaching the athlete to land properly in order to finish the landing from a jump. So what you'll see in this particular lab in real time, assuming that the template comes up in real time here, is a vertical ground reaction force, the acceleration of the center of mass, vertical acceleration, vertical displacement of the center of mass, as well as the muscle activation of the rectus, and as well as the gastrocnemius. So you get knee extensors and plantar flexors, and you can look at the timing in which these muscles occur. So this is a pretty straightforward lab. You'll be able to do this in probably about 15-20 minutes, and you're essentially going to be comparing counter movement jumps and to that of the squat jump, basically comparing all these metrics that you see here between the counter movement jump and the squat jump. Now, as an aside, a year ago, one of our undergrads did an honors project looking at the validity of the My Jump app and another similar mobile app, and using our motion capture system and force platforms as the criterion method to which these apps were compared. And we found that they had good reliability and good concurrent validity. In fact, the error between the app and the criterion method using motion capture was within 5, in some cases 10 centimeters, which is pretty high, but most of them occurred between, you can see here, looks like between 2 and 5 centimeters. So it was pretty close and had good reliability. Okay, so for lab 6, as I mentioned, you will be comparing jump performance metrics such as jump heights, vertical ground reaction force, the vertical displacement of the center of mass as measured with the motion capture system, and EMG. So you'll be using both the My Jump app, which I have the videos posted up on Canvas and how to use it. It's actually fairly straightforward, as well as the motion capture system. So this is a standard Hill and Hayes marker set you see here. Clean them as you usually would. Make sure that they're nice and clean, that the timelines are good to go. Let's see here, looks like for this group, yeah, it looks nice and gapless. And then for this particular case, you do not have to manually identify the events, but you need to make sure that your setup file has the correct events. So if you click on Tools, Biofeedback Event Timeline, you'll see this, and you should see start, takeoff, landing, and end. If you don't, that means you're probably using an older setup file. So just in case, if you do not see these event definitions, you can load them by going to File, Load Setup, Load Event Definitions. And I had already put these into your Spring 2020 folder. Go to Support Files, click on Jump Track, and click on Setup Jump Track Events. And I already loaded, so I'm not going to load it again, but just click on that, hit Open, and then you are going to save that setup. Like I said, I already have it here, so I'm not going to do it. Okay, so you don't have to do anything. You don't have to manually do this. It's going to do it automatically. And the way you do this automatically is you go to Layout, and let's do left and right. And then here on the right side, you can either click F10 or Presentation Graphs. Now I already have the correct presentation graphs that's going to be used for this lab, but more than likely you will not see this. You probably see something different. If so, right click anywhere here. You'll see this window. Click File, Load Graphs File. You're going to go to Roar KinLab, Cortex File, Jump Track, and you are going to load this Jump Track EMG graphs. Okay, load that in there. when you click on, in fact, let's do this from scratch. I am going to close graphs file. I'm going to open or load this graphs file. This will be under, let's see, where Google Drive, PLNU. You should go to Rorikin Lab. All of you have access to this. If you're in the lab, go to Cortex Files, Jump Track, and we're going to click this first one, Jump Track EMG Graphs. Okay, it's going to load, it's going to do its thing, and the first tab you should select is GRF, right here. Notice it's blank. It should automatic load. In fact, once all the ground reaction force data gets populated, the events should occur or should be identified automatically for you. I made a script to make sure that it does that. If not, just hit calculate and it'll populate automatically. So once you look at that, go click on this tab, acceleration, and you can see all of the data is already here. And once you're done, hit save, capture. You're going to do 5 counter-movement jumps, or you're going to collect and clean 5 counter-movement jumps as well as 5 squat jumps. Make sure you see all this. Once you have all the events, then like before, go ahead and generate the C3D files so that we can bring them into Visual 3D, and ultimately you'll get a report. For this particular team, we haven't outputted the other jumps, but I can see here for trial 1 for counter-movement jump, and trial 1 for squat jumps. You'll see jump heights and the vertical ground reaction force. But you have to clean all the data first in Cortex.